right, welcome. So in this video, I want to talk about the backpropagation algorithm, which is quite a famous algorithm for training artificial neural networks. Sort of with the backpropagation algorithm, artificial neural networks really started to become a powerful tool for artificial intelligence researchers. So I want to start by introducing, so when was backpropagation first introduced? Well, there were some seeds of backpropagation earlier on. Remember, neural nets and perceptrons, as they were sort of originally called, or neurons were originally called, were discovered and then sort of dismissed a little bit earlier on in the history of artificial intelligence. But in 1986, the backpropagation algorithm was introduced by this gentleman, Geoffrey Hinton, and a couple others, David Rumelhart and Ronald Williams. They really started a repopularization of artificial neural networks, and by the time I started doing artificial intelligence research, or the first time I sort of encountered artificial intelligence in my own studies was about 1999. Backpropagation with artificial neural nets was really popular and had spread all over the place. Not surprisingly, for this contribution, which was a very important contribution to computer science, in combination with the contributions made by Yoshua Bengio, I think I said that right, and Yann LeCun, they have all won the most prestigious award in computer science, which is called the Turing Award. Let me fix my slide there that said the Turing Award, of course by accident. The Turing Award, which is awarded to computer scientists every year for outstanding contributions to computer science. Recently, it has been going to some artificial intelligence researchers and some cryptography researchers in particular. These have been areas of computer science that have been honored recently, and this particular contribution was for deep neural networks, a topic that we'll get to in a future video. But one of the main parts of a deep neural net is the backpropagation algorithm, which we're going to look at right now. As I mentioned, it was quite popular in that period of time, still very popular for training neural networks. It is usually applied to a standard kind of neural net, the kind that we've really been talking about a lot in these videos, which is feed-forward networks. So remember, feed-forward networks are ones where we kind of have some layers and we go from the beginning to the end. There's a front and there's a back. There's an input and there's an output, and then there's some sort of discrete number of layers in between. Now that we don't always have to stick to fixed layers and fully connected and so on, but often the kinds of networks that we do use the backpropagation algorithm for are exactly those kinds that have discrete layers in the network, maybe as depicted here, one hidden layer or 2, 3, 4 more hidden layers, and then each layer is fully connected to the next and not connected to any other. So the input layer is connected to the first hidden layer. All connections that could exist do exist, and then the same for the next layer. The hidden layer is connected to the next hidden layer if there is one. All connections that do exist or could exist do exist, but again, no connections except other than those adjacent layers. So this particular network structure was popularized because of the backpropagation algorithm and its success, and then it sort of took over. It's not the only kind of network structure you can use for your neural network, surely not, but because backpropagation is so successful with it, it is a very common network structure. The word backpropagation, or the name backpropagation, comes from us applying a similar rule where we calculate sort of the error that's applied to the output layer, and then we propagate it backwards. We send it back to the hidden layer, and we sort of say how much each of the neurons in the hidden layer contributed to the error on the output layer. And then once they know their error, again, we can pass it back and pass it back. If there's multiple layers, we can continue to pass that error back. As we do, we use that error to adjust the weights in a reasonable or rational way, or specifically following the gradient descent algorithm that we reviewed in the last video. So we're going to use gradient descent to try and get us towards the outputs that we want. So in this video, we're going to help us sort of understand what's going on, we're going to explore a very simple example. And so we've sort of been looking at these XOR neurons. So again, a very simple neural network. So simple that we typically wouldn't actually build this other than as a hello world to neural nets, or as we're doing here as an explanatory example. So in this particular neural net, we might have the input layer with two inputs that are going to be binary inputs. We're going to expect zeros and ones, and we're going to attempt to compute the XOR function. So we want to have the appropriate output given a particular input. And for this example, we have to start somewhere. When we start our backpropagation algorithm, we're going to start with some weights. We have to pick some weights. And to get us started, I just sort of randomly, kind of semi-randomly, just assign some weights here. 0.9 is coming into this neuron, a 0.4 and a 0.3 coming in to this one, and again a 0.7 and 0.9 coming into this one. Somewhat arbitrarily chosen. We could have picked different ones, just needed something to get the example going. Now, the first thing we need to do in the backpropagation algorithm is backpropagation algorithm starts with the error. And to get the error, we need to know what is the current performance of the network. So what we do is we expose the network to some inputs. So in this case, I've chosen the 1-1 input for the XOR gate. And we're going to expose it, and we're going to pump it through, do the math. So again, you can verify here. What I've done is I've pumped this through with these weights, and then I've applied the standard sigmoid function with no adjustments to get the activation value of 0.86 here and 0.67 here. Again, usually we have finer resolution with our numbers. We usually have a couple more digits, of significant digits that we might keep when computing. But for our example, I'm going to keep them small and sort of simple. So then we're going to take the outputs of these hidden layer, and we're going to pump them through, again weighted by 0.7, 0.9. Again, run it through a sigmoid function, same sigmoid function here, to get our activation. And our output activation in this case is going to be 0.77. And so right away we can see that's probably not good. Our input was 1, 1, and what we want our output layer to do then is give us a 0. That's the expected output for the XOR gate, and we're quite a bit off. We're at 0.77. All right, so once we have our gate performing and we know what its current value is, we can perform one iteration of the backpropagation algorithm. What we're going to do is we're going to apply backpropagation over and over again to different inputs and adjust the weights over and over again in a gradient descent to hopefully find a minimum point where we minimize what? Well, we want to minimize the error. We want to minimize how much error there is from our actual output and the expected output, the one that we want. Now, how you measure error is always going to be kind of up to you. And so we sometimes call this error function, we call it the loss function in this context. And so we're going to need some kind of loss function that tells us what the error is. A very straightforward one that we can imagine applying right away is we can imagine saying, okay, we know that the expected output here is 0, and the actual output is 0.77. So in some sense, the error is 0.77, or maybe minus 0.77, depending on how we want to calculate that. But that error, that magnitude, we might treat as the error. But there are other things we can do to compute the error, and this is a very simple network that only has one output neuron, so that was a real easy metric for us to sort of come up with on the fly. Whereas if you have maybe 10 output neurons, 100 output neurons, you might have to come up with something a little more sophisticated. The other thing that's going to be required here is what's called supervised learning, and we've kind of been hinting at that already. Supervised learning means that we need to know what the expected output is for the inputs that we're using to train. If we don't know what the expected output is, then that would be a case of unsupervised learning, where we just give them inputs, but we don't know what the right answer is. Then we might need to use a different algorithm. Backpropagation requires supervised learning. All right, so let's talk a little bit about a loss function. So the one we're going to use in this example, and a commonly used one, although there are alternatives, is the mean squared error function. So what we're going to be doing is computing for all the inputs that we might have, outputs that we might have here. So this is output 1 up to output n. We're going to be computing, again, L for the loss function, the sum of their squared differences. Okay, so the mean squared error is going to take that same error that we just computed on the cuff. where we said, okay, expected output 0 minus the actual output of our neuron. So in our case, our I is 1, or our N, sorry, is 1. We only have one neuron in our example. So in that case, we would take the 0 minus the 0.0 or 0.77, which will give us minus 0.77, and then we square it. And squaring it, sure, it will squash that negative for us, which is convenient, okay? But it's also going to amplify some of our differences, the larger ones in particular. And then, so we just sum them all together for all of our neurons. So we might have already anticipated that, okay, we could compute the error and we could add all those errors together. If we don't end up squaring them, say we could take the absolute value instead. That's a different metric that we could use. If we don't end up taking the absolute value, we might get negative errors canceling out with positive errors, and we wouldn't want that. That would make it seem like we don't have error maybe when we actually have a lot of errors. And so that's one of the other reasons why we like that squaring, is it makes sure all of the error calculations here are positive. There are a couple other reasons why we like this function. One of them is it's differentiable. It's also easily differentiable. Since we're going to use it in the gradient descent algorithm, that's very convenient. I just mentioned it amplifies those large errors, which is going to be good. And then this is the shape of the function. This is the two-dimensional shape of the function. The one-dimensional shape is just a simple parabola, but we can generalize that. As we go up to however many dimensions that we need, the shape in that kind of dimensional space, 10 dimensions, 100 dimensions, whatever it is still going to be a big old parabola like this. And what is it that we like about that? One, it's got the nice slopiness feature that we use in gradient descent. We can go and descend. Now, unfortunately, we're going to compose this function with other functions, and that's going to cause more bumpiness. So this one has no local minimum or minima at all. It only has one single minimum, and that's if we use this function, and this was the only function, we could easily find that minimum. But unfortunately, as I said, we compose this with other functions, the activation function in particular, which cause it to change its shape. But it's still, at least this function has this nice shape that when we compose it with the other function, it allows it to keep applying that smoothiness. Maybe it doesn't have one minimum anymore, but again, hopefully it has a nice smooth descent towards that minimum, or the one minimum that we're looking for. So those are some of the reasons why we like this function. It's not the only good function out there. Okay, it also performs well in certain statistical cases. But a lot of the things that we use neural nets and backpropagation for, especially in modern days, is to classify things into categories. So for instance, imagine image classification, which is a very standard application of neural nets. We might have a bunch of different images, let's say images of animals, and we want to classify them by the kind of animal. So this is a cat, this is a dog, this is a horse, this is a frog, whatever it might be. We have all these different animals, categories. Maybe we have 125 categories or something like that, and we want to classify all our pictures into those categories. This kind of categorization task benefits a lot from using a class of functions called the cross-entropy loss functions, where what the cross-entropy loss functions actually do is compute sort of the differences between the categorization. So how many dogs did you categorize as cats or frogs or whatever, and calculate that sort of that off difference. And that can be really useful for training models to do those specific kinds of tasks. So we're going to use this one here. Why? Because it makes the examples a little bit easier to work with. Again, it is a very common loss function, but for other tasks we might use other loss functions as well. All right, so now what we want to do is we're going to try and apply the gradient descent algorithm. And to do that, we need to know gradients, which is the slope or the direction that we need to travel. And in the gradient descent video, we explored a one-dimensional case and a two-dimensional case. But in this case, we're going to have one dimension for each of the weights that we have available, and perhaps more, because there may be a few other things we need to differentiate on as we propagate backwards. But at the very least, we can imagine ourselves as having 6 dimensions that we might want to compute our gradients relative to. Each one of these weights is a weight that we might want to adjust just like we wanted to adjust one of those components of our point in our vector space when we're applying the gradient descent algorithm. So let's think of ourselves as having a 6-dimensional vector space. Each entry in one of those vectors at the least, our weight vector, are these numbers, 0.9, 0.9, and so on. And this is actually sometimes a way that we actually implement neural nets is by keeping these kind of vectors and multiplying vectors by other vectors, because effectively that's what we're doing. The input vector is being dot product with the weight vector. Okay, so we need to compute gradients of the loss function, that's what we just looked at, relative to each of these variables. So we're assuming here when we say this that the loss function must be a function of those variables. Okay, so we can think about the loss function. The loss function was a function as we stated it on the last slide, as it was a function of output neurons, or our output neuron here. Well, that output neuron's activation, its expression, what was coming out of it, is a function of its weights, which are a function of these outputs, which are a function of these weights. So in a very long, complicated way, we can write the function as this really big, ugly function of lots of different variables. Now, we don't usually write that function down, even though what we're going to be doing in the backpropagation algorithm is performing the derivative of that function over and over again. Luckily, we're just doing that numerically, so we don't have to compute something symbolically that's kind of ugly and nasty. All right, so we're going to start with the taking the partial derivative of the loss function with respect to its its variables, which are the output neurons. So again, remember here, we've got O1 to ON, and we've defined our loss function to be this. But say we're now focusing in on one of our neurons, and we want to know, okay, what is the error on this neuron, this particular neuron, or the loss, and we want to then use that to adjust the weights that this neuron uses as its input weights. So we're going to focus on that one. We're going to call that one, say, OI, or pick whichever one you prefer here. We're going to pick that one. We want to focus on that one. And we're going to notice that all the other terms then, since we're doing a partial derivative, all those other variables, we're going to treat as constants. So all the other terms in this sum are all constants. So there's only one specific one. I'm calling it OI, one specific OI. And we're going to pick that one out, and all the other terms are constants, and taking the derivative of them, they disappear. So we only need to worry about one of these terms, EI squared, and the 1/2, remember, is still there. We're going to bring it in. And we're going, maybe I didn't mention this, but we intentionally put the 1/2 there on purpose, so that when we compute this derivative, the 2 that's going to pop out front is going to cancel out. It just cleans up the output here. Also, later on, we're going to use a learning rate. We're going to multiply this by sort of an arbitrary weight, an arbitrary number. So we think of this constant as not really being as important. We can put this 1/2 here, which makes our derivative really nice, and then later we can just undo this with our learning rate if that's what we needed to do. So it's not going to affect our output. So that's why we have that 1/2 there. It's going to cancel out. Sure enough, we see it happening right here. And then the other thing we're going to notice, well, we had that negative in there. Applying the chain rule very simply, we need to take the derivative of the inside there. We get multiplied by -1. So we actually get a -1 out front. Some presentations of the backpropagation algorithm are going to omit that -1 altogether and just pretend it's not there. Others are going to absorb it into this term and say OI minus EI. If you multiply this in, you just swap the order of those two terms. So depending on which presentations you're looking at, you might see slightly different versions of this, and you say, hey, wait, that's slightly different than what I saw in that video. Maybe they're using a slightly different notation. So keep that in mind when you're looking out at other implementations. Okay, so we've sort of computed this value now, but now you notice when you look at this, the error, this is the expected value minus the actual output. In our example, that would be 0 minus the 0.77. Since it's 0 minus 0.77, that gives us minus 0.77. And then with the minus out front, flips it over and gives us 0.77. So this turns out one of the other reasons we like using this particular loss function is it means the value we need to compute for the derivative, the slope of this particular part of the function, is just that straightforward error that we might think of as the error, the difference between the output of the neuron and its actual expected output. So for all these reasons, it's easy to compute and it's easy to express and it's straightforward and it makes sense when we kind of plug it into our own brain as the error between the neuron and its expected error, that makes it really easy to compute and practice. And so it turns out this is just one of the components of the gradient that we're computing, but this one is pretty straightforward and easy to compute. All right, so we're going to move to the slightly trickier one that we need to compute. So let's look at our activation function. So for our activation function here, I'm going to use the sigmoid function, or the logistic function as my sigmoid function, I should say. And in this case, I'm using the simple parameterized version that has ones and zeros and all of the straightforward parameters. So for instance, you notice there's no k out front here. We're not subtracting anything off from the object value. We've just got our sum, our weighted sum, and we're taking e to the minus of that power. Okay, so a straightforward logistic function. Now, why am I also pointing this out? If you start putting parameters in there and changing them up, you've changed your function. And if you change your function, you're going to change the partial derivative. So using different activation functions, even just different versions of the logistic function, is going to mean changing the backpropagation algorithm. And of course, maybe you're using backpropagation with a different activation function. Go out there and look it up. Someone else has already used that activation function and probably has a tutorial to show you, what the gradient looks like for that activation function, which might be different. Now, the other thing is, at this point, it's pretty nasty. It's an activation function of a lot of different variables, and this activation function I'm using sort of generally right now, but we know that each of our neurons has its own activation function. In your model, they might have different activation functions. That's common in some neural networks. So depending on which activation function you've got in each layer, in your neurons in each layer, might determine you have to using different rules in each layer. So again, this is just an example of one activation function, but again, it's a pretty common one. And if you are using other logistic function variants, you can probably straightforwardly modify this version to work for your variant. All right, so one of the things that is making this a little nasty right now is just all those variables. So I'm going to do a little bit of substitution in for our big old weighted sum. Let's sort of abstract that away for a second. So I'm just going to call that whole big weighted sum function of wi's or wj's and hj's, and I'm going to call that u, and that way I can rewrite my activation function. Okay, now that's looking like the logistic function, sort of the simpler one that we're used to, and that might be easier for us to do some differentiation. All right, so to get started with computing this derivative, I'm going to just do a little bit of manipulation algebraically. We're going to multiply the top and the bottom by e to the power u. That's just going to get rid of that extra e to the minus u down there. You can double check my algebra here to make sure that we end up with this slightly different function, e to the u over 1 plus e to the u. Now, if it's been a while since you've done some derivatives, you can go double check that we've got a rule for a case like this, which is called the quotient rule, where we're computing the derivative of a quotient, and I'm just going to apply this here. So we're going to get derivative of the first multiplied by the denominator, and then we get subtracting off the numerator multiplied by the derivative of the denominator all over the denominator squared. So I've just gone ahead and plugged that rule in, applied my simple derivatives that I needed to, and multiplied them out, and we got this function here with a little bit of simplification. Again, double check my math. We get to this state here. This is the derivative of the activation function with respect to u, at least computed straightforwardly for the first time. This format is still not exactly the one we have it in the algorithm, because it's not exactly the easiest to express in code this way. Instead, we recognize, oh, that kind of looks like it's like the activation function we're already using, the one we already use, 1 over 1 plus e to the minus u is very similar to this. While there's a little bit of differences, it turns out that with a little bit of algebra, and you can definitely double check my algebra on this one, that you can take 1 minus that activation function, multiply it by the activation function, and it gives you the derivative. And this is a real nice quality of the logistic function as an activation function, is its derivative is also kind of straightforwardly expressed. Not as straightforwardly arrived at. To get here, we had to make a few extra steps, but once we have it, it's actually pretty straightforwardly expressed. So again, what is AU here? A is the activation function itself, the sigmoid function, the logistic function. So we just apply it. So this is the actual activation of our neuron. We just take that activation and we multiply it by 1 minus itself, and that will give us the gradient at this particular point. So what we've done here is we've computed the derivative of the loss function, and we've also computed the derivative of the activation function. But actually in the true function, the true loss function that we're trying to compute, the OIs that we were using as our variables were actually standing in as the activation function for output neuron OI. So we had our original expression of the loss function was L of O1 up to ON. But each one of those is actually the activation function applied to its own input, which I'll call here UI up to UN. And so we can see that the loss function is actually composed with the activation function. We've got the activation function inside of the loss function. Now, that makes the loss function kind of nasty to write down, but it makes it actually not that hard to compute the derivative of thanks to the chain rule. So we can apply the chain rule to this. So we've sort of gone on the outside, we've got L, on the inside we've got A. So we can think of the chain rule here as being F and G. What we're going to do is we're going to get the derivative of the outside calculated with the output of the inside. So remember, when our G of U is A of U, the activation. We're actually plugging in the activation into the derivative of the loss function here. And then we're going to compute the derivative of whatever's going on the inside of our chain rule, the G. So in our inside, that's the activation function. So really, the two terms that we've computed, this was the derivative of the loss function, plugging in for that value, the OI value, the activation, the actual value that is output by that neuron. That's the first component. Okay, remember that -1 we've got there again. Remember, some people ignore the -1 and add it later. Other people carry it for the ride. For our purposes, I'm bringing it along. And then the right-hand side here, the next two terms, well, that was just the derivative of the activation function that we computed. So at least relative to UI, we still have a few more derivatives to compute, but at least relative to UI, we can compute, and UI just being the inputs, the weighted input to that neuron, we can compute its gradient. So this term here, we often attribute it to the neuron itself. It's not at this point the gradient relative to each of its individualized weights. That's what we want to compute. But at this point, we've computed it up to the neuron, and we still need to go one step further to compute it for each of the weights. But because all of the weights share this same value, and in computing the contribution to each of the weights, we need this value, we often give it its own name, and we carry it along for the computation part as we call it the delta for this neuron. So in this case, I'm calling it delta OI, or the delta for the output neuron I. Okay, so we have enough information now that we can compute our delta for our output neuron. So we had already fed forward our data. We had got the output of 0.77, and our expected output is 0. So we can compute the first term, the derivative of the loss function, by just taking the expected output minus the actual output, and we already did this one. 0 minus 0.77 gives us negative 0.77, and then multiplying it by the negative gives us back 0.77 again. So that's one of the components that we need to compute, and we, in this case, it just happened to be the actual activation. I guess that's what happens when your expected output is 0. We can also compute the other component, which is the derivative of the activation function. Now remember, what that was the activation function at, taking into consideration the input. So what is that? That's 0.77, the current activation of this neuron. And then we multiply it by 1 minus that current activation. So doing that, we get, what is that? 0.23, and we get the value 0.18 as the actual gradient, sorry, not gradient, but the derivative of the activation function. That's the second component that we need to consider in our delta. So finally, we can put them together and compute the delta for the O here. We just multiply those two together and we get 0.14. Again, the precision on my numbers here is not very high. That's just to keep our example kind of wieldy, but in real calculations, you're going to use much more precision than this to make sure that your numbers don't accumulate a lot of error, which is what's happening on my example right now. So if we want to apply the delta rule in the output neuron to determine the contribution that each weight made, we just need to push that derivative one step further by differentiating the last component, which was the u that we were using as our substitution, relative to the weight in question. And let's, again, maybe just pick one of our weights arbitrarily here. I'm going to call it weight j. So now let's assume we've got our ui function and we're going to compute the derivative of ui relative to weight j. Well, since it's just a simple weighted sum, it's very straightforward to see that all the other terms, we're taking the partial derivative again, so all those other terms become constants, they're all thrown away, and the only term that has the term we're concerned with is wj hj, and taking the derivative of that just gives us hj. So to finalize the gradient, we just take the delta of that neuron and we multiply it by the output of the neuron that's coming in along that weight. So whatever, in this case, we're worried about weight j, so we're worried about the output of hidden neuron hj, because that's the one that comes in along that connection. So if it was firing off a lot, then that means we're going to change this weight more because it made a greater contribution. If it was firing off very little, then that means that this weight didn't make a very big contribution, and so we won't change this weight as much. So that's really what's going on here when we're multiplying by hj, is we're adding that last bit to the gradient to see how much this weight contributed to the error on this neuron. Okay, now I mentioned this is what we're going to adjust. So in our gradient descent, we're going to use this gradient to adjust weight j, wj, in the output neuron. But we're not going to do that at this step. And that's because we need to continue to go backwards in the network, computing gradients of previous steps. And we don't want to do that with new weights. We want to do that with the old weight. So we're going to keep going using the current weight. So we're now going to compute the gradients of our hidden neurons. We still need that derivative of the loss and activation function because, well, in particular the activation function, because that's the one that we're going to use the same activation function in these neurons. Again, if you used a different one, you need a different one then. And then the other thing we need is we need to backpropagate or propagate back the error or the loss from this node. We're going to use the delta to do that into these two nodes to try and determine how much they contributed to that error. Now for these nodes, it's the opposite of what we just did for the weights. We now want to compute the gradient with respect to the actual input so that we can pass that on into that particular neuron. So the input in this case being hidden neuron hj, we want to know what its contribution was. So now instead of tracing out and getting hj as our derivative, we're going to trace out the hj and getting wj as the derivative. So taking the partial derivative with respect to hj, we end up getting the weight. So what does that mean? Well, when we were trying to figure out the contribution of this weight to the error or the loss, we multiplied the delta by the output. But now we want to figure out what the contribution of that output was to the loss, and so we multiply the delta by the weight. And again, if you've done this a few times, you start to realize, okay, this is kind of straightforward. We do one for one and one for the other. But it's really, we've got that same delta term showing up again, and you can start seeing why we keep the delta term, as its own little term, because we apply it in more than one spot in our calculations, and instead of recalculating it every time it's convenient to keep it around. Okay, so this is the gradient. This now tells us, so this here was just the derivative of this u function with respect to the hj, but putting it all together, multiplying it all together, just means applying the chain rule again. So we're just, every time we apply the chain rule, we multiply another term on this big long derivative chain. And so now we've got the derivative of the whole loss function with respect to hidden neuron j. Okay, hidden neuron j. So actually, we only did this, the way we computed this right now was also relative to output neuron I. So we can see this was delta OI. So this is actually the contribution that HJ made to the error only on on output neuron I. So actually, if we want to know the whole contribution that this neuron made, we need to sum the contributions from all of the output neurons. So we now iterate, we do this same calculation for all of the output neurons that are connected to this hidden neuron, which again, in most fully connected networks are all of them. So we would now need to compute the sum of all of them and use that as our starting value, or the loss value that we might use in now computing the delta for the hidden neurons. Okay, so we'll start with this contribution. This is the contribution going back. And now what we need to do is say, well, what's going on in this hidden neuron? Well, this hidden neuron is also applying the activation function. So that means we can now apply the same technique by multiplying this term hj. That's just the output of hidden neuron j. 1 minus hj, that's the other term. Putting those together, that gives us the derivative of that hidden neuron, or the activation function of that hidden neuron. So we've got the sum as being the contribution from the output neurons. That's the loss bit. And then we've got the activation function bit right here. Again, this gives us the delta of this hj. And we can then again use that to compute the gradients using the same technique that we just did for the last two, relative to its inputs. So we can go back and look relative to its weights, and that means just computing or multiplying by the input value. And if we ended up having more networks back, so here I'm assuming the layer before the hidden layer is the input layer, so we only have one hidden layer. But if we had multiple hidden layers, we would just have the next hidden layer backs nodes here, and we can keep applying this process as we go back. All we're doing is doing more iterations of the chain rule, which just means adding more terms to the big long chain that we sum up. Okay, so let's get back to our example and try and compute the deltas for our hidden neurons. So we now have two hidden neurons, and we are going to use the delta value. So this sum now, because we only have one output neuron here, the sum, we only have one that we're summing over. That makes things a little bit easier for us in our example. So we're going to take the delta value of our output neuron, that's our 0.14 that we computed earlier, and we're going to multiply it by the weight, so in this case 0.71, and then we're going to, so that's going to be the loss contribution of this part to delta, and then then we're going to finish it off by taking the derivative of the activation function, which is just taking this value, the 0.86, that's the hj, and multiplying it by 1 minus itself. So again, making sure we got all these terms. We got our 0.14 term, we multiplied it by the weight, we took the activation term, we multiplied it by 1 minus itself. Computing that out, we get the value of 0.12. And then for the second hidden neuron as well, we're going to just do the exact same process. We got the 0.14, the 0.9 is the weight, the 0.67 multiplied by 1 minus itself gives us the delta for that neuron of 0.028. Then what are these values? These values are just used to compute the contributions made by these weights to the overall loss or error up at the top. And one thing you might notice here is that the delta values that are computed on this hidden layer are actually quite a bit less than the ones that were computed on the output layer. This can be common, which means it takes longer for the error to propagate back. especially smaller errors. And so this is why neural nets might take many training runs to propagate back, especially depending on their depth. Sometimes, at least for some of these naive, straightforward neural nets, just using backpropagation out of the box, as it were, for considerably deeper networks, you are looking at much longer training times, which usually means that those networks are not as feasible for whatever it is that you plan to use them for. So that's just one of the reasons, because propagating that error back is going to diminish that error to some regard, which is also by design. We expect that the amount of error that each of these nodes contributes should be less than the error of the actual node itself. Okay, so we've got some delta values there. We've now, for our very simple network, we've computed the delta values for all of the neurons involved. Remember, our input neurons here are just passing the input along. And so for all of these relative values, we're going to now be able to compute updates for our weights. So that's the last bit. Well, I said there's an extra step here. If you have more hidden layers, keep going back, so keep propagating back. But then otherwise, we now adjust the weights using our computed gradients, and we're just using gradient descent now. So we just need a learning rate to tell us how much we want to move them. So again, what do I say? What do I mean when I say we're just using gradient descent? Well, we've got a weight here. That's one of our variables in our vector space, and the vector that we're using in our gradient descent. And we've computed the derivative in that dimension, in that direction, because this is one of our dimensions. So we've already computed that its contribution, or we can at least, by multiplying the output of this neuron to the delta value, and that's this formula here, and we just need the learning rate. Now, I've chosen to use the learning rate at 0.5 for this example. Why? That's just going to amplify the changes made a little bit. Remember, we're using very low precision over here, so it's hard to see those changes unless they're pretty big. It's not as common to use a learning rate this high. You might, depending on your application again, but more common learning rates are maybe smaller, like in gradient descent, usually 0.1 or a little bit less than that, depending on how fast you want to approach that minimum without overshooting it. Okay, remember that's what the trade-off there. So we're going to apply this now to all of our neurons here, just multiplying the delta value by the activation of the incoming neuron and using that plus the learning rate to adjust the weight. Now, because we're doing the minimization, again, we're doing minuses here. So we're going to apply that. So let's do the first output neuron here. So again, starting with the original weight, we subtract off the contribution. We take the learning rate, we take the delta value, and we take its output activation. Now you'll notice here that at least for this neuron, all the incoming ones are going to have the same delta and will usually have the same learning rate. And so what that means is we're weighting the changes of the weights based on how strongly the associated neuron was firing. So since this first hidden neuron was firing more, 0.86, then this one 0.67, the change we're going to make along this connection is going to be bigger than the one we made along this connection. So we can indeed see that we did 0.7 and we adjusted it down to 0.64. That's a change of 0.6, whereas the other weight, even though it was a bigger weight, it had a smaller contribution thanks to its neuron firing less. It gets a smaller adjustment to its weight, well, 0.5 instead of 0.6. Again, I've amplified these changes for our example, but even the amplified versions are kind of very close together, the 0.6 and the 0.5, or 0.06, I should say, and 0.05. Okay, so those will be the weight adjustments for these ones. Again, we move back. We've already got our delta values. Once we have the delta values, there's not much more we need to compute, just multiply them out. Luckily, on our next two neurons, the inputting values are just 1. So we're assuming they're both coming in as 1, so that makes this really easy. Notice here also, if the input value was 0, what would that mean? That would mean there would be no change to the weight, and that contributes sometimes in cases like this. It's one reason why we might want to adjust those inputs so that they're not a flat 0, flat 1, but maybe are off by just a little bit. So in this particular case, we've got again So this is the first hidden neuron here. We've got our delta value. We've got that input value of 1, as I mentioned. Again, we'll notice here both of our input weights are the same, so we end up both with the same starting and the same ending. But because both of the input neurons here had an input of 1, we end up with the exact same change in both these cases. The other thing we'll notice here is the change is only 0.01, and that's because we've changed the size here of our delta value by about an order of magnitude, which is quite a bit. So again, let's do this for the second one. Same thing, we've got different weights now, but because we've got the same inputs coming in, they get changed by the same amount. So both of them are going to end up with the same adjustment of minus 0.01. So we end up with these weights, so we can go ahead and change the weights now. So after one application of the backpropagation algorithm, we've now adjusted our weights. And usually the next thing we do at this point is we pump through the network now to see what happens. So in this case, we can use the new weights with that same value, and we can see that our output changed from a 0.77 to a 0.75. Again, a kind of small change. Well, remember, it takes many iterations usually to train a network, so we've only done one of usually thousands of iterations. So at this point, that's a pretty good change for this one output. Now, we've also only trained it on, or we've only done this for one input, 1, and we should train it on all the possible inputs, all 4 of them. If we only train it over and over again on 1, all it's going to learn is what the right output is for 1. And we need to iterate it usually through a range of different inputs to make sure that it is not just, we call this overfitting, or learning just one thing, the one thing we're telling it to learn. We want it to learn something more general so that when we're done training it, we can go apply it to other things, other inputs, and hopefully it will work on them as well. Now for the XOR gate, that's kind of strange. If you've got it working for the 4 inputs, it should work for all the inputs coming in. But again, we don't usually use the XOR, we don't usually make XOR gates out of neural nets. This is just an illustrative example with a really small network. So what do we use the neural networks for? We more commonly use them for image detection or image classification, and this is both a traditional task used for neural networks, but then also something that it's really good at and has been deployed at, especially very recently, quite popularly. And so this is a very, this is an example of sort of a task we might have. So this is a classic example coming from the 90s where due to computational, or not having as much computational power, we tried to focus on smaller tasks that were easier to classify. So one easier to classify task are sort of very small grayscale or black and white images of handwritten digits. So that's what we have here is a bunch of handwritten digits that were written, maybe written in scan or written on a classic sort of device. These particular ones have actually gone through a couple stages of pre-processing, which makes them a really nice set of images that can be used for machine learning, and we in fact use that a lot. And as we've mentioned before, these are used in backpropagation and other supervised learning cases. So supervised learning are cases where we need to have images that we already know what the expected output is. So for this particular example, we might imagine that the first row is part of a set that's all been labeled 0, and then the second row has been labeled 1 and 2 and 3 and so on. Meaning that some ambiguous ones like this little 4 here, that maybe if in a set by itself you might think, is that an A? I don't know. And some of these 7s have crosses on them and so on that might maybe make them look like a 4. These will be pre-labeled, letting us know what they are, so that when we feed them into the algorithm, or backpropagation needs supervised learning, but other algorithms do as well. When we feed them in, we can tell them this should be a 7, this should be a 4, whatever it might be. And so because algorithms like backpropagation require supervised learning, and because supervised learning needs these sets of images that are, like I mentioned, kind of pre-processed. One of the pre-processes is making sure it's centered. The other one was to add what's called anti-aliasing. So the original set only had black and white, which was a kind of a it's not really a normal image for hand-drawn symbols, and so anti-aliasing adds some grayscale in for pixels that probably should have a little bit of gray, a little bit of the black on them, but not all black. That's called anti-aliasing. So that kind of pre-processing. So there's been a lot of pre-processing to make these images good to work with for machine learning algorithms, and as a result, researchers keep them together. So this particular set that I pulled from, I got this image from Wikipedia, but it's a Wikipedia article about this really well-used, well-popularized set of images called the MNIST, or from the MNIST database. These ones, as it says here, these are 28 by 28 pixels. So 28 by 28 is already pretty big, and if you're just multiplying out, think that we're going to have one input neuron for each one of these pixels. And the original set had only black and white, so that those could be binary inputs, right? But now, as I mentioned, they've been added grayscale, so now usually it's about a byte, I think. I'm not sure how they're represented in this particular database, but a byte would allow you to have 256 scales of grayscale if you need it, and that's usually sufficient for whatever you're using it for instance, RGB graphics. And so even with that, you know, what we were saying there, 28 by 28 pixels for each one of these images. Each one of those pixels is maybe going to be a byte. And then this database has tens of thousands worth of these images. So that it's a really, you know, in the 90s, it was really hard to store a set this large. So that's why we shared them in a larger database that could be accessed by many researchers. And then now in the modern day, well, we do the exact same thing, but just with much more massive sets of images, the kind that are being used to train the image detectors of today, and also some of the generative art image AIs that are now becoming popular. You may have noticed in some of my videos here, I've been using AI generated art from the Midjourney that uses neural nets similar to this. So as I mentioned, these sets are very common in machine learning. One of the things that we use them for is benchmarking. So because a lot of papers have been written using this particular set of images, and you know, so-and-so says we got accuracy 95% and it took us this many, you know, training runs. Another group comes out and benchmarks by saying, well, we got this much accuracy and this many training runs. And it's, you know, it's not necessarily a competition, although of course it is. We're all trying to improve optimization, but it's a way to measure our algorithms relative to one another with a standardized set. So this isn't the only standardized set of images that are out there, but this one is, I mentioned, it has 60,000 training images, and then there's also on the side 10,000 testing images. Now what does this mean? Well, it's common in supervised learning, and again for backpropagation for neural nets, that we're going to train it with a bunch of images. So for instance, these ones here, and we're going to tell it this is a 0, this is a 1, and we're going to get it to a point we're maybe going to stop when its accuracy gets really high, let's say 99%. That's really good accuracy. So say we get it up to 99% accurate, then we might turn around and give it a new image from the testing images, the 10,000 testing images, and if it got trained really, really well, that really all it did was memorize this set, the set that we gave it. So it's so good at that set, it might actually not be very good at new ones, because it hasn't, this is a new one, I've never seen this one before, and all I really did was memorize every single input, and that's what we call overfitting. And so to test our machine learning models, artificial neural networks in particular in this case, we reserve some of the data that we have, that labeled data that we need for supervised learning. We keep it off on the side, and then we use that as testing data afterwards. So we train them on the 60,000, and then we test them on the 10,000. And we use their accuracy on the 10,000 to determine how good the model is, not their accuracy on the training set. And that's because the accuracy on the training set should be high. That's the whole point. We want to see how well they do once they perform out in the real world. And that's, again, very common in these types of supervised learning, machine learning examples or algorithms. So let's take a look here. I want to now say, so in this case, I actually made a Python algorithm, and I actually borrowed it from some others on GitHub and modified it ever so slightly. And this is just to train the XOR network. XOR network again is used maybe as like a hello world for neural nets. And so in this case, what I've done is I've run this little Python program, and I've run it with the initial weights and biases. Since in our example we use no biases, just to make all the math a little bit easier, and I just have less variables floating around. I'm going to start off my simulation here with 0 biases. They actually do have biases, so the biases are updated in the exact same way, treating them as just normal neurons. So in this algorithm, even though we're starting them off with weights of 0, their weights are probably going to change. And so what happened? So I ran them on these particular weights, and I ran it for 10,000 epochs. So an epoch is usually how long we, or what we call one of our training runs. And in a training run, we usually expose it to all of the inputs that we have available. So if we were using the MNIST database, we might have 60,000 tests in our epoch. In this particular example, since we're just doing XOR, we only had 4. We only did 4. So I did 4 10,000 times, and we trained it on each of those 4 and adjusting its weight for each of it each time, trying to see if we could get it into a network state that would solve the XOR function. Now, one thing we'll notice here is that so maybe we'll start with the performance here. This is the 4 inputs, so 0, 0, 0, 1, 1, 0, 1, 1. So we're expecting 0, 1, 1, 0. That's the output that we want to see here, 0, 1, 1, 1, or close to. Since these are neuron outputs, we're expecting 0 point something here and 0.9-ish something up here. That's what we're looking for. What we can see here is it's not bad, but it's not great. Okay, so what do I mean by that? Well, for the ones that are 0, in the last case here, it's actually still firing off 0.22. Now, luckily, if the way we were using this network was we were just rounding it, then we would be getting the right outputs here. This would round down to 0, and these ones would round up to 1, and we would get 0, 1, 1, 0. So for that reason, I'm going to count this as a success, but it's maybe not the best success, okay? We can imagine it doing better, certainly. The other thing we might just do is look at the weights. I'm not going to spend too much time nitpicking the weights here, but they're kind of interesting. The hidden weights are coming in at 2626. That's interesting. They've got, the first one's got a real strong negative bias of minus 3.7, and the other one's got minus 4.9, so I'm not really sure what's going on there. But then one of those hidden neurons weights is got a real strong negative, the other one with a real strong positive, and our output is just predisposed to being negative. Maybe that's how it's trying to get these zeros on with a bunch of other energy pumping in for the ones. So interesting network. I'm not sure how it works necessarily, but we can see that it does work, and that's common. I want to sort of inspire you to do this. Don't look at a neural net and say, oh, I understand how this works. It's kind of like reading the matrix sometimes. Even for these simple XOR neural nets, they might not be working in a straightforward way that a human brain's going to think out, but that doesn't mean it's not working in some way. And sure enough, this one looks like it's performing well enough that if we were rounding these outputs, we would be doing well. So that was just my first trial run. I wanted to try it on the weights that we set up just to see what would happen. But I want to use this to sort of show, again, some of the challenges working with backpropagation with neural nets, and in particular with gradient descent as it's being applied here in backpropagation. So the next one I ran, so I just went to my terminal and I changed it from those starting weights to random weights. And I ran it. My expectation was it was going to be better because most of the time that I ran it with just random weights, it did really well. But I wanted to show this one because it shows us that even with random weights, we might get in a place where we get caught in some kind of local minima. So one thing that we'll notice here is my last one. Okay, so actually, if we rounded this one, if we rounded it, this would go down to 0, this would go up to 1, this would go up to 1, and this would go down to 0. Okay, we might call that a success. For this XOR, this might be good enough, and we might count that as a success. But when I look at it and compare it, for instance, to other networks that do XOR, I can see that this is, there are certainly better networks than this. This last one with a 0.47, that's basically right in the middle. If it was having to decide between two different categories, it's basically saying here, I don't know which category it's in, and that's not, that doesn't give me confidence, okay? And so I'm looking at this one thinking this is not a very good one. So it kind of got stuck in some minima. Is it stuck? I don't know. I'd have to run it for more epochs. And I have tried this. I can set my epochs for 100,000. I've done that, and I usually get good ones. But again, I usually got good ones for 10,000. The difference between 10,000 and 100,000 on my machine, at least, was 10,000 is as soon as I press enter, I get the output. But 100,000, I got to wait for a second or two. So that's why I decided on 10,000. Let's look at a couple other ones. So this is another random start, but this is more typical. This is what I would normally see. If I just kept running it over and over again on a random start, this was much more common. And see what kind of error or loss we're kind of getting here. This is a good one, 6%. We got about 6%. We got a little bit, less than 6%, and 5.5%. Though that's the kind of error that I want to look for on my neural nets, right? This says to me that this network is pretty confident in its output and it works well. I would deploy this one, say this is my XOR net. If I needed a neural net that did XOR, here you go, here's one that does it, okay? Now I say here you go, here's one that does it, because if I ran it again, I might get the exact same kind of performance, but I might get a completely different neural network. And again, how does this neural network work? I'm not really certain, and I'm not going to put in a lot of effort in trying to analyze it, what it's doing. It looks familiar, like it kind of looks like some networks I've seen before, but again, I'm not going to put a lot of effort into trying to figure out. It's sort of like opening up a brain and trying to figure out how a person's thinking by looking at it. It doesn't make as much sense. That's why what I am focusing on a lot are the outputs here, because that's the behavior of the network. That's what we can see. That's the part that we know how it should behave. Okay, what other ways to start it? Well, one way you can start out your network is with all zeros. So random is a way to start it, but I remember being told this anecdote by one of my AI professors a long time ago. But the idea is, if you're sort of a grad student, you're working on this, and you want to decide, should I start it with random inputs or random weights, or should I start it with something fixed like all zero weights? What's better? And the answer to that is never, unfortunately, just a hard yes or no, or we would have told you already. It's usually contextual, so it's better in a certain case. So random can be better because it's like starting at an arbitrary point. If you don't know where to start, just start somewhere random, because it's as good as any other point. And as we just saw with a couple of our runs, it allowed us to, if we ran it a few times, if we get some good random ones, we'll get some good ones and we'll train the network out the way we want. The problem with the random ones is if you did get good ones and you did get to a good point, and let's say you just got really lucky, they just happened to be the one sets of random ones that were good, it can be hard to remember where you started. You don't know where you were. You just randomize them. You can't go back and get them. So write down your random number. So if you get something good, you can remember what your random seed was. That's a good lesson. But the other side of that coin is sometimes it's good to start off at some point that is fixed, that you already know where you're starting. And if you have no better point to start, then start at 0, 0. That's sort of what I'm saying here. Start at the origin 0, 0. Now let's think for a second. We can see already that this gets stuck in a local minimum. So the output of this network is 0.5, 0.5, 0.5, 0.5. Now why is this a local minimum? Well, if we looked at the graph of the actual loss and activation function, I don't know what it looks like, but what it has here is a very shallow kind of minima, which means any point around it points back to it. So if it tries to adjust itself out of this minima, it gets sucked back into this minima. And on top of which, this is where we started it. We started it on this minima. Okay, so we started it with absolutely no input and no output. And what does that mean? It means our output neuron has its input value of 0, and when its input value is 0, it just spits out 0.5. So that's why we're getting 0.5s out, and the loss function cannot the loss function has a minima right here, and it's stuck here, so it cannot adjust this out. So even though I ran it for 10,000 epochs, it never changed anything. Okay, so this is an example of zeros, maybe not so good. Not a great place to start your backpropagation probably. Maybe 0.1 would have been better. I didn't try that one, but what I did do is I tried ones. I said, okay, what happens if we started them all at ones instead? Now remember, also a difference between zeros and ones is zeros are no input at all, which means if you think back to our backpropagation algorithm, that means no changes to their weights. Well, that's why they didn't change, right? Ones at least has some signal, which means it gives it something to change its weight. So we put some ones in here. So 0 probably bad, 1 is it better? Well, let's take a look at the output. The output is not that great. It's stuck in another local minima. It's not the same local minima, but it kind of looks similar to the one that our first random run got stuck into. We're doing all right on the first one, but these other ones are at about the 66% or the 2/3 area there. And that says to me maybe there's another local minimum right around that point, and it's having a hard time getting out of it. The other thing about these local minimas in the high dimensional spaces, it might be a minima relative to some of these variables, but not the other one. But the other ones might have a very, very shallow gradient. So we've really just got a whole bunch of gradients here that are really close to 0. And maybe there's one that's going to slowly bring us towards where we want to go. But because its gradient is also very shallow, we're facing that diminishing gradients challenge, and we might just not be able to optimize away from this point. All right. So I hope you've enjoyed this exploration of the backpropagation algorithm. I know it's a little bit complex, so we had to get into some math there at points, but now I hope you have a nice deep understanding of the algorithm. You might be able to apply it yourself in your own coding, or maybe using some of the popular neural network libraries that are out there. So once again, thanks a lot for watching, and we'll see you in that next video.